In this video, we're going to cover the quotient rule. You'll notice the quotient rule and the product rule have very similar comparisons. So, in terms of the quotient rule, we're again going to have two specific functions, say f of x and g of x, and we're going to want to have them divided such that we're taking the derivative, d dx, the derivative of this function, in respect to x. Now again, notice how this parenthesis here setup is situated. Now, this particular situation, again, there is another proof for this, but we'll do that in a separate video. The derivative of this entire function will be the derivative of the top function times the bottom function unchanged. That should sound familiar. Again, the derivative of the first times the second unchanged. But this time we're going to have a subtraction sign between the derivative of the bottom function times the top function unchanged. However, for the quotient rule, there's going to be a division by the bottom function squared. So this is the formula. Now again, we're going to do the same thing we did with the product rule, and we're going to try and drop all these x's and get them out of my way so I have some placeholders. So we're going to have d dx, or of f over g, is the same thing as f prime times g minus g prime times f, all divided by g squared. Now keep in mind, once I've done this, these are now just placeholders for f, g, g prime, and f prime. And again, keep in mind, these little dashes here are the derivatives. This is actually a power. So, if we look at a function, and again, I'm going to do the same thing I did in the last example for the product rule. I'm going to call this function f of x, and this function will be something along the lines of 3x squared minus 2 divided by x plus 1. So in this function, you'll notice we can't actually simplify this division. So the quotient rule is absolutely necessary for us to be able to take the derivative here. Again, I can't just simply divide term by term because there's multiple terms in the denominator. This cannot be simplified in any way to make it easier for us. So what I'm going to do, however, is I'm going to call this top stuff f. I'm going to call this bottom stuff g. I'm going to go ahead and set up the same thing I did before. F is 3x squared minus 2. I'm going to go ahead and take its derivative and get 6x and nothing more. I'm going to go ahead and identify that g is again the x plus 1, and therefore g prime is just 1. Again, the derivative of 3x squared is, bring down the 2, is 6. 3 times 2 is 6. And then x to the power of 2 minus 1, which is just power of 1. The derivative of any constant goes to 0. Derivative of x is 1. And the derivative of 1 is 0. So here is all the pieces I need to plug into this formula. So I'm going to go ahead and do so. If this is f of x, again, this is the problem we were given. F prime of x will be equal to f prime up here. Notice again, my f prime is a notational thing, so this f prime here. So I'm going to have 6x. I'm going to put it in parentheses so I don't make any silly mistakes. Times g. G from here is x plus 1. Minus, because that's the formula, g prime is just a 1. I'm going to put that in parentheses even though it doesn't need to be there. I know that this one is extra, but what if this wasn't just an x? What if this was, say, 7x? Then this would be a 7 and I would need the 7 here. Or what if this example was more complicated entirely? Get yourself into the habit of putting every single one of these things in parentheses. So my next thing here is f, and f is 3x squared minus 2, so I'm going to put that in parentheses as well. This is all divided by the function g squared. So g is x plus 1 down here, x plus 1 quantity squared. Now in this case, I will definitely clean this up a little bit because the problem is not actually terribly obnoxious in terms of the algebra. So the 6x here will distribute to both those terms, giving me 6x squared plus 6x. I'm going to throw that back in parentheses. I'm going to go ahead and say that this is minus all of this stuff. When I try and simplify this, you'll notice that that positive 1 distributes to those two if it needed to, and that would leave you with a minus 3x squared minus 2. Again, notice I'm throwing it back in parentheses. I'm simplifying just the individual terms, this one here and this one here, and then I'm leaving that minus sign there, making sure I do everything I can to be very careful with the multiplication as well as this negative in the middle. Keep in mind now at this point I'm going to go ahead and distribute that negative to all the terms in the second piece, giving me 6x squared. I don't need the parentheses anymore once I've done this. Sorry, make sure you distribute the negative here to get negative 3x, and the negative to here to get the positive 2. This is all divided by x plus 1 quantity squared, and I will go ahead and clean this up by adding the like terms together. 6x squared minus 3x squared is 3x squared. There's only one single x term and a single constant term, and therefore this is the actual derivative function for f. Again, be very careful. This is the formulaic notation. It's the derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared. Assuming you have, again, a function on top and a function on the bottom.